All right, so hello everyone, and I'm very happy to announce Gorjan Radevski, who's a consultant of ours, and he's going to present our work, compositional steering of large language models with steering tokens. Gorjan is consulting our human-centric AI group, where he works on LLM alignment, steering, interpretability, and other topics. He completed his PhD at KU Leuven in Belgium in 2024 under Professor Tine Tuitelaars. I hope I didn't butcher her name too much.
That's okay.
And he was focusing there on multimodal learning across NLP and computer vision. His work has been published at top-tier venues, including NeurIPS, ACL, EMNLP, and ICCV. So without further ado, Gorjan, thanks a lot for taking the time to talk to us. And yeah, the floor is yours.
Okay, then I'll start. Can you hear me well?
Yes, we can hear you.
Okay, good. Yeah, so as Kirill said, I'm Gorjan Radevski, and I'll present compositional steering of large language models with steering tokens, which is a work that we submitted to ACL and we're now waiting for the reviews. Okay, to dive in, our motivation is to shed some light on the compositional steering problem. That is, the large language models in general, they need some ad hoc behavior control, meaning that sometimes we want to modify their behavior at runtime, and sometimes we want to modify their behavior at runtime according to multiple simultaneous constraints. Now, in order to do this, we have few options, and each of them has its own trade-offs. So, one thing we can do is we can perform fine-tuning if we know these constraints or behaviors upfront, which is expensive on one end, and on the other end, it can destroy the generality. What I mean by destroying the generality, technically, any fine tuning we perform will have an effect on the general knowledge that the language model has. Another alternative is just like prompting, something that we are all used to. But also, as we all know, it's quite brittle and inconsistent, meaning that just different wordings or different phrasings of how we specify the behavior could lead to different outputs of the language model. Then there are some techniques which fall into the prompt compression domain. Some of these are activation steering and, for example, GIS tokens, and these are quite good actually for single behaviors. But they essentially fail to perform composition of multiple behaviors, which is what we address in this work. So essentially, the gap that we attempt to fill is that there is no effective representation for the concept of the composition itself, and this concept of the composition will allow us to perform steering for multiple behaviors simultaneously. So our proposal, or the method that we propose in this work, is compositional self-distillation of steering tokens. Our pipeline is in two stages. In the first stage, we train individual behavior steering tokens with self-distillation, where the teacher is essentially the language model with the instruction, conditioned on the instruction to be exact, while the student is the language model, which is conditioned on the steering token. Then in stage two, we freeze these individual behavior steering tokens, and then we train a specific end steering token or a specific compositional operator on two behavior combinations to learn this composition that we want to encode. Additionally, as I'll explain, I'll provide more details later on. We do some orthogonality regularization to prevent collapse and to obtain better performance. So overall, the bottom line from this slide is that the language model always stays completely frozen, so we don't modify any of the existing parameters, and we only learn a single vector for each behavior that we want to encode, plus one additional vector for the composition operator or this end steering token. So in stage one, as I said, like our goal is to perform self-distillation of these individual behaviors, where essentially, again, the teacher will be conditioned on the instruction while the student will be conditioned on the steering token. What's important is that both the teacher and the student, they are an instantiation of the same language model, meaning that they share parameters and they remain frozen. Then the teacher is conditioned on the instruction tokens, which in this case could be answer in one sentence, while the student is conditioned on the steering token, which is again a single vector. And in this case, the goal of the steering token is to encode the meaning of answer within one sentence or reply within one sentence, and so on. Then when we measure the loss, we measure the loss on top of the answer tokens, where we essentially the loss is the per token KL divergence loss. Now, more formally, we train a single embedding per behavior. The language model is frozen, where this distillation loss is essentially the knowledge distillation loss between the teacher and the student, where the teacher is again conditioned on the prompt tokens and the instruction, while the student is conditioned on the prompt tokens and this behavior steering token. Yeah, technically, I think I covered everything on this slide. So in stage two, assuming that we have already trained this individual behavior steering tokens, now we want to train this compositional operator, or to learn this compositional operator. In this case, what we do is we freeze all of the behaviors, individual behavior steering tokens, that they won't be modified anymore. And then we'll train this end token only on two behavior combinations. And on top, we'll just add this orthogonality regularization to prevent the collapse. In terms of the teacher and the student, everything is the same. It's the same model, same instantiation, frozen parameters. Again, the teacher is conditioned on the instruction tokens, while here these instruction tokens are essentially combinations of two different behaviors. The student, again, will be conditioned on the steering tokens, but what's different here than the individual behavior training is that here we'll have the end token will be trainable, while we'll also include individual behavior steering tokens. However, we will keep them frozen, such that this end token will just learn the meaning of the composition. Again, the loss will be computed on top of the answer tokens. And again, so formally, we freeze all of the individual behavior steering tokens, and then we train only the embedding for the end token, which is of dimensionality D, and D is the dimensionality of the language model, and we train it with KLOS. The input to the model will be the embeddings of the prompt tokens, the embedding of the first behavior, then the embedding of the end token, and then finally the embedding of the last behavior. While the total loss is the knowledge distillation, and this orthogonality loss just scaled by some scalar. Now, in terms of the orthogonality loss, our goal with this orthogonality loss is to essentially force this end token to be dissimilar from the individual behavior steering tokens. By doing that, essentially, we ensure that this end steering token will not interfere, and it will span a different subspace. And we see that empirically it works really well, and we have a separate ablation for this. In terms of the experimental setup, so we test this approach on 17 verifiable behaviors. What I mean by verifiable is that we don't need to use some LLMs judge method in order to see whether our steering method will push the language model towards the behavior that we want, but rather we can automatically verify it. So we use different languages that we can automatically verify, different lengths of words, so which we can also automatically count. Same goes for sentences, and then different formatting. By formatting, I mean like lowercase, title case, start each word with a title case, or just like uppercase of the entire answer. So yeah, I mean, you can see the examples here. Like, for example, for the languages, we might have answer in German or reply in Spanish and so on. then use 3 sentences, like reply in 1 sentence, reply in 4 sentences, and so on. And for the formatting, it could be something like each word in your answer should be title case. We split these behaviors into seen and unseen, while we have 11 seen behaviors and 4 held out unseen behaviors, where we have 1 per group. What I mean when I say unseen, it's essentially when we train the end token, the end token will never be exposed to these unseen behaviors. And this allows us to essentially just test the compositional generalization, because in the future, we don't want to retrain this end token for each new steering behavior that we want to encode, but rather we just want to train this individual steering behavior, and then the end token should work as is. Now, this unseen split of behaviors, actually, how we can achieve it, where we can combine one seen token and one unseen token, and then we'll have an unseen combination, or we can combine two unseen behaviors, and again we'll have an unseen combination, or we can scale up to 3 combinations where one of them will be an unseen behavior, and we'll get an unseen combination. Then we have 4 model families that we test with. So different sizes of Quen models, Llama, and some open source models like Small and Olma. In fact, all of these are open source. And then these models are with different scales. So it ranges from 3 billion to 14 billion parameters. The metrics that we measure is the average accuracy of how often we satisfy the constraint or satisfy the behavior. Then average of the max of the order variance, because if we change the order of the instructions also, or if we change the order of the steering tokens, that will have an effect on the accuracy, and we want to see to what extent this varies, because we want to improve on that as well. And then the response quality, which we measure with an even larger Quen model, a 30 billion parameter Quen model, to ensure that by performing this steering, we don't degrade the response the response quality of the model itself, because that is something that we want to retain. As baselines, we do steering using prompt instructions, and then we also perform merge of LoRA adapters. That is, we use the exact same training pipeline. It's just that instead of storing the knowledge in the steering token, we store the knowledge in the we encode this behavior within a LoRa adapter, and then we perform fusion of this. And then we have a few steering token variants. That is a concatenation, so without this end token, then a composition with the end token, which is the default, and then a hybrid version, where essentially we have both the steering tokens with the end token, and then the instruction. And in total, we do around 1 million evaluations per experiment, because of the different combinations, plus like around 1,000 samples per experiment. So it's quite a lot. Now, in terms of the findings, what's relevant from this table? I'll try to be succinct. So concatenation will essentially concatenation is in general inferior compared to composition. However, on these 3 behavior compositions, we'll see that it completely collapses. So if we see like the concatenation of steering tokens without the end token has around 33 unseen accuracy, while if we do composition, we'll get up to 59, and it's the same pattern for 2 behavior compositions, both seen and unseen, while we mainly focus on the unseen, because that's the most important part. Then we also see that composition beats instruction steering on unseen by around 5% on both 2 and 3 behavior compositions. And this is usually not the case for regular steering vector approaches. While we see that, for example, if we compare a composition of steering tokens with the end token against instruction steering, we see that in general, we improve on top of it. And then finally, we see that hybrid, it's essentially the best overall. That is, the steering tokens and the instructions are complementary. And in general, across 2 behavior, 3 behavior compositions, and all metrics, combining these 2 approaches yields the best results. And then finally, like if just like a side note, let's say, if we merge the LoRa adapters, we see that they fail to generalize to unseen combinations, where we see that, for example, even compared to instruction steering, it's a severely degraded performance. Furthermore, if we explore the robustness across different model sizes, we essentially what we did is we took three different versions of a Quen model, so 4B, 8B, and 14B. And the overall trend, without diving into a specific number, is that performance will improve and order variance will decrease with the model size. So meaning that the model, not the model, but rather the approach scales well with the model size. And as you can see here, for example, on unseen behaviors, we go from 69 to 76 to 78. And then if we go to three behavior compositions, again, we go from 58 to 62 to 69. So performance improves, and also like the order variance will decrease if we look at these columns. And yeah, finally, like the best hybrid approach that we observed is a 14 billion parameters Quen model, which will reach 69.2 performance with 6.2 order variance. And the last, or maybe most important, also takeaway from this experiment is that two behavior training will suffice. Generally suffices. What I mean is that we also tried training this end token on both 2 and 3 behavior compositions, and we saw that there is no performance improvement really. For example, for the 8 billion Quen, we'll see that both are around 77, let's say, and for the 14 billion Quen, also the performance is quite similar, and even for the two behavior only training, it's even higher. And this is a general trend for both 2 and 3 behavior compositions. And why I'm saying this is the most important takeaway, because this essentially means that by training this end token only on two behaviors, we kind of like managed to learn a more general compositional operator that can essentially combine different number of behaviors. Now the issue is that we didn't test more than 3, which I'll mention during the limitations at the end. In terms of an ablation study about the initialization of the end token and this orthogonality regularization, as I also mentioned in one of the previous slides, so this end token is quite essential, and without it, especially unseen performance just drops to 49. While if we see like all other different initializations and different versions, as in with the orthogonality loss or without, just beat this number across the board. And then this orthogonality loss, which allows us to have an end operator which is different or orthogonal to the individual steering tokens, also brings large gains, especially on unseen. This is the most relevant part, because if we see, for example, on seen categories, that is categories with which we train this end token, there is essentially no improvement, and performance it's even a bit worse if we train with this regularizer. While on these unseen categories, we see that it is absolutely essential. So performance without it, it's just severely degraded, and same goes for the order variance. It's just higher across the board if we don't have this orthogonality regularizer during training. And the final takeaway is essentially that this the zero initialization and this orthogonality loss is just the best trade-off from accuracy and order variance, while we get the highest order, the highest unseen accuracy with the lowest order variance if we initialize with zeros, and then we have the orthogonality regularizer. So last but not least, in terms of like we do some pair behavior breakdown, where essentially we try to see like for different models on which combinations it fails. Here we've added just like the 14B Quen model at the top, and the 8B llama at the bottom. And overall, like if we look into these specific pairs, we see that each architecture has kind of like specific failure modes. Well, the main takeaway from this slide, without needing to read all of these small letters, is that hybrid steering, or the rightmost two columns, it just eliminates these failure modes, and we see that across the board, our method, when combined with text instructions, will beat the text instructions across all of these different categories, meaning that these two are complementary, and we can effectively use them in practice. So the last slide, some takeaways and limitations. So overall, I learned compositional operator and will outperform instructions and just other steering baselines, with no loss in the response quality, meaning that we retain the general coherence that the language model has when generating text. And this hybrid method, where we combine the steering tokens in the instruction, it's consistently the best. And then finally, we scale across different model sizes, and we generalize across different model families, even though this table is not part of the slides. In terms of the limitations, so we only evaluated these automatically verifiable behaviors or automatically verifiable constraints, while in general, steering will be more applicable for something like generate text that is politically correct, or whatever, some more abstract behaviors that we didn't test yet. And then we tested only up to 3 behavior compositions and 40 billion parameter models, while if we scale up to higher order compositions, 4, 5, and so on, and some frontier scale models, will also be like a cool experiment to check and explore. Thank you for your attention.